The memory in our system is volatile. That means when we power off our computer, all of the information in memory disappears. To be able to retrieve that information later, we need some type of device that's able to maintain that data even when your system has no power. Fortunately, there are many different ways to accomplish this. We could have a hard drive, a solid-state drive, a flash drive, a memory card, an optical drive, and other storage devices as well. One of the most popular forms of storage is a hard drive. This is a magnetic device that has rapidly spinning platters that are inside, and all of your data is being stored onto those platters. This is a random access method of storage, so we can store information anywhere on that drive and access that information immediately by simply accessing the address where that information is stored. If we were to look inside of this hard drive, we would see there were a lot of different moving parts. For example, there are platters inside that are spinning around thousands of times in a minute. You have a moving arm that is able to take a small head that reads and writes information from these spinning platters. And there are also other mechanical components that are then moving the arm back and forth. Because these are mechanical, any one of these components could potentially fail at any time. You obviously don't want to remove the top of your hard drive because this is an area that needs to remain dust-free. Inside your drive, though, are components that are very similar across all hard drives. One of these is the spinning platter, and that is where all of your data is being stored. We also have a spindle in the middle that is spinning the drive at different speeds. We'll look at those in a moment. We also have an actuator that is able to move an arm that has at the end of it a read-write head that is actually performing the reading and writing of that information to the platters that are rapidly spinning just underneath it. Different hard drives spin at different rates, and if you look at the specification for a drive, you'll see that it probably rotates at 5,400 revolutions per minute, 7,200 revolutions per minute, 10,000 revolutions per minute, or 15,000 revolutions per minute. The reason there are differences in these revolutions is that the arm is in one place. We have to wait for the platter to spin around to be able to read the data that needs to move underneath that read-write head. The faster that spindle rotates, the lower the latency will be, which means we'll be able to read or write information faster if we're on a 15,000 RPM drive versus a 5,400 RPM drive. From the side view, you can see that often there's more than one platter. This drive has multiple platters where information is being stored. And if we were able to look underneath, we would see that there is an actuator arm and a drive head, not only on the top of the platter, but also on the bottom of the platter. There are also different sizes of drives. Inside of a desktop computer, we don't have to worry too much about the size of a storage drive because we have so much room to be able to store that inside of that unit. But if you have a laptop or other mobile device, having a smaller storage device is going to save you that much weight and that much space in that mobile device. If you're working on a desktop, you may be using a 3.5-inch drive. You can see the size of that is listed here, and the 3.5 inches refers to the width of the drive. There's also 2.5-inch drives. These are common to see inside of mobile devices and laptops. And on modern computers, you may be using an SSD that doesn't use a 3.5 or 2.5 inch. Instead, is a much smaller 22 millimeters in width. Many of us have upgraded our hard drives to SSDs, or solid-state drives. These contain non-volatile memory inside, which means there are no moving parts, thus a solid-state device. A significant benefit of having solid-state drives is its raw speed. Solid-state drives are many times faster at reading and writing information than a traditional hard drive, so by simply replacing a hard drive for an SSD, you can greatly improve the overall throughput of a system. And if we remove the top of an SSD, you would see that we don't have any moving components inside. In fact, most of the components that we're able to see offhand are simply the memory modules where your information is being stored. When we moved from hard drives to SSDs, we immediately saw an improvement in performance, but we also saw that we were hitting the maximum limit of what a traditional SATA connection would provide. We needed some way to increase the throughput of these SSDs, and one of the ways we did this is to connect the SSD directly to the PCI Express bus of our computer. One of the most common ways to do this is to use an adapter card where we can install the SSD on the card itself and plug it directly into the PCI Express bus on our motherboards. This meant that the motherboard was providing the power and giving us the throughput that we now can get from a PCI Express bus, which is much faster than the bus that we had connected to a traditional SATA drive. Instead of limiting ourselves to the 6 gigabits per second that you would commonly see with a SATA connection, plugging into the PCI Express bus allowed us to get speeds of around 64 gigabits per second per lane. This greatly improved performance, and we were able to take advantage of the full throughput available to that SSD. But of course, not every device has a PCI Express bus that you can connect to. Laptops, for example, don't allow us the room to be able to install a full-size adapter card. If we were to look at the SATA technology that we're currently using for hard drives, it uses a standard called AHCI. This is the Advanced Host Controller Interface. This is the standard used to move data from the drive into memory and back again. If you were to look at SATA Revision 3, it provided throughput for the SATA connection up to 6 gigabits per second. But as we've already seen, that value is much too low to be able to provide the total throughput that we could get from an SSD. To be able to increase the speeds of these throughputs, we created a new method of communication referred to as NVMe. This is the Non-volatile Memory Express. It has very low latency and can support higher throughputs because it is directly connecting to the PCI Express bus, even if that bus is one that's inside of a laptop. A very common interface into this PCI Express bus on a laptop or desktop computer is made through a new interface referred to as the M.2 interface. And if you are using NVMe on this M.2 interface, you now have a theoretical transfer speed of approximately 20 gigabits per second, which is obviously much better than the 6 gigabits that we had from the SATA connection. But in some cases, we are still using these hard drives inside of a desktop, and we still need a way to improve throughput to the information that's on those hard drives. To increase this throughput, we've added a new method of communication referred to as Serial Attached SCSI, or SAS. Serial Attached SCSI is a serialized version of the SCSI technology that we've been using for many years. So now we can take advantage of the SCSI protocol to be able to control and manage the data that's on these drives. And by upgrading the communications path to be a serial connection, we can now reach speeds of approximately 22.5 gigabits per second. And this is obviously much faster than the 6 gigabits per second than you would commonly get from SATA. And we expect that future versions of Serial Attached SCSI will even provide faster throughputs than what we're seeing today. Here's the interface on a Serial Attached SCSI drive. There are two different connections on this drive, one that's used for data and one that's used for power. And if you look at this drive, it looks very similar to the configuration you might see on a SATA drive. In fact, this is very similar with the data on the left side and the power on the right side. If we were to put a SATA drive right on top of this drive, you can see that indeed they are very similar to each other in their form factor. However, you will notice that the SATA drive and the SAS drive are slightly different in the connectors that are used. This is to prevent you from accidentally plugging a SATA drive into a SAS drive configuration and vice versa. So if you have large storage arrays of spinning hard drives, you may want to focus on using SAS arrays with SAS drives to get the highest throughput possible for that hard drive technology. As our storage technologies continue to shrink and our interfaces to those technologies needed to become even faster, we considered a number of different interfaces to be able to connect these systems to our desktop, laptops, and other devices. We were obviously already using SATA as a standard, and this is a representation of a 2.5-inch SATA drive, and we created two other types of interface technologies, one called mSATA and the other referred to as M.2. mSATA refers to Mini-SATA. We took the connections that were on our existing SATA drives and moved them into a form factor that was slightly smaller with our Mini-SATA. mSATA was a great stopgap between the traditional SATA drive connectivity and the eventual M.2 interface that we began to use, And we found quickly that instead of using mSATA, many manufacturers were including M.2 connectivity on their motherboards and mobile devices. mSATA did solve a number of problems, especially size on a system board and connectivity to a higher speed bus. The M.2 interface has become a very popular interface for most of our storage devices, especially SSDs. There's no additional cables that you need for data or power, and that M.2 drive plugs in directly to the M.2 interface on your system board. And since we are directly connecting to the bus of your system, we can take advantage of PCI Express speeds to increase the total throughput to these storage devices connected to an M.2 interface. Different M.2 interfaces will support different types of connectivity, and the way that we differentiate between these capabilities are with small keys that are associated with the drive connection itself. If you look at the end of the drive, there'll be a small spacer at the bottom that is called either the B key, the M key, and some M.2 drives will support both a B and an M key. Other M.2 interfaces may support the much faster NVMe interface, so it's important to know what type of interface is available on the system you're connecting to. Some M.2 interfaces will use these keys to designate what type of throughputs are available, so you might want to check with your system board or motherboard documentation to see if it supports an M key, a B key, or both. Here's a closer look at an M.2 drive that supports both the M key and it supports the B key. This means that this hardware can plug into any device that does have availability for either M-type connectivity or B-type connectivity. This also makes for a very fast installation or removal. You simply slide it into the interface slot and fasten it down to the system board. Flash drives are a very handy way to store information into a very small form factor. They consist of EEPROM memory, that's electrically erasable, programmable read-only memory. This memory is non-volatile, so you can remove it from your system and the power source, and all of the information stored on that flash drive will continue to be available. EEPROM is a technology that allows a certain number of writes, but at a certain point, it will stop writing that information to the drive. You may still be able to read the information from that drive, but you won't be able to write anything new to that drive going forward. We don't really consider flash drives to be very good archival or backup media for a number of different reasons. Not only is the EEPROM limited as to the number of writes, but it is a very small storage device and it's very easy to lose these. This is one of the reasons we always recommend that if you're storing information on a flash drive, that you also have a backup stored in another location as well. USB flash drives you'll find being used almost everywhere, but there are other types of flash drives as well. One of the original and now relatively large types of flash storage is the compact flash, or CF. SD cards for secure digital are often used in mobile devices, and if you get into very small devices, you may find Mini-SD or micro SD being used. And if you have an older digital camera, you might find that it uses flash drives in the XD picture card format. We don't tend to see optical drives used very much in our production systems these days, but there is a lot of information that we've stored through the years onto this optical drive format. Optical drives are using small bumps that are written onto the drive itself with a laser beam. This is storage that is microscopic in size, and we're able to store a great deal of information on a single optical drive. Because of this method of writing information and reading information using a laser, these tend to be relatively slow when you compare them to a hard drive or to an SSD. But since optical drives take up very little room and store quite a bit of information, they were a very good choice for archiving data for later. You may find optical drives using the formats of CD-ROM, DVD-ROM, or Blu-ray, and there's often either a built-in optical drive reader or something that can be plugged in externally to be able to read these drives. If you have some older optical drive archives and you need to be able to read this, you might want to grab an external optical drive reader and plug it into your system using a USB connection.